What if I told you we could build a ruler that could actually measure the ripples in spacetime, or a camera that could see the magnetic field of a single molecule inside a living cell? This isn't science fiction anymore. We are right on the edge of a revolution in measurement, a new kind of technology that lets us see the world with a precision we once thought was fundamentally impossible. And this quote, it really gets to the heart of it all. If you look back through history, pretty much every major scientific leap, from discovering new planets to figuring out the atom, it was all unlocked because we found a new way to measure things or just got more accurate. It's simple, really. We see farther when we build better tools. So here's our game plan for today. First, we're going to talk about a fundamental wall we've smashed into when it comes to measurement. Then we'll see how quantum mechanics itself gives us the key to break right through it. After that, we'll dive into the absolutely incredible new universe this all opens up. And finally, we'll get real about the challenges of bringing this tech out of the lab and into our worlds. For all our amazing progress in building sensors and gadgets, we've come up against a wall. And this isn't an engineering problem. It's a hard limit baked into physics itself, telling us exactly how precisely we're allowed to observe the universe. This wall actually has a name, the standard quantum limit, or the SQL. Just think of it as a baseline level of noise, of static, that's just part of reality because of the rules of quantum mechanics. So when you use old-school methods to measure something, like, say, shooting a stream of individual photons at it, you just can't get any clearer than this fundamental fuzziness. Here's another way to think about it that I really like. Imagine reality is this super high-resolution digital photo. Well, the standard quantum limit is like a fixed grid of pixels laid over that photo. It doesn't matter how amazing your zoom lens is, you physically cannot see any details smaller than a single one of those pixels. Anything below that level just gets lost in the blur. Okay, but here's the brilliant twist. The very same quantum rules that create this limit, well, they also give us the tools to completely shatter it. It turns out that all that weirdness from the quantum world is actually the key to unlocking a whole new level of precision. So the crucial difference here is how we're probing the world. The classical way uses a stream of totally separate, uncorrelated particles. It's like throwing a handful of pebbles at a wall one by one. Sure, each one gives you a bit of information, but the randomness creates this shot noise. It's a fundamental static that caps your precision. But the quantum way, it uses particles that are entangled, which means they're linked together, their fates are intertwined. By using these connected particles, we can get super clever and cancel out that random noise, letting us measure way, way beyond that old classical limit. And one of the most powerful tricks in this new toolbox is something called quantum squeezing. So picture the total uncertainty of any measurement as being like the water inside a water balloon. You can't actually make the water disappear, but you sure can reshape the balloon. Squeezing lets you push down on one part of it, the uncertainty in something you don't care about, which then forces the other part to bulge out, dramatically narrowing the uncertainty and the measurement you do care about. It's so clever. And this all comes together in a pretty straightforward 3-step process. First, you prepare it. You create one of these special quantum states using entanglement or that squeezing trick. Second, you encode. You let that delicate state interact with whatever it is you're trying to measure. A magnetic field, a gravitational wave, whatever. And that process encodes the signal right onto your quantum state. And finally, you measure. You perform a final measurement to read out that encoded information with, you guessed it, incredible precision. Okay, so we can break the old limits. That's cool. But what does that actually let us do? This is where things get really exciting, and the applications are just mind-bending. We're talking about everything from the scale of the entire cosmos all the way down to the inner workings of our own bodies. So, let's start big. At the largest scales imaginable, quantum sensors are literally becoming our new eyes and ears on the universe. They're helping us listen for the absolute faintest whispers from the most mysterious events and substances out there. I mean, a perfect real-world example is the LIGO Observatory. It was already an engineering masterpiece, right? It detected gravitational waves. But then, by putting squeezed light into the system, that quantum trick we just talked about, they smashed right past the quantum limit. And get this increased the volume of the universe they could search by a factor of 8. That is a massive, massive leap in our power to observe the cosmos. All right, so from the biggest things out there, let's zoom all the way in. The same exact principles that let us see distant black holes merging are also about to completely revolutionize medicine by giving us a brand new window into the very building blocks of life. Because these sensors can be microscopic, they can measure things with unbelievable spatial resolution. We're talking about being able to probe the tiny magnetic fields around a single neuron as it fires, or detecting the presence of just one molecule that might signal a disease. This could open the door to totally new kinds of medical diagnostics that we can't even dream of right now.
And the impact just keeps spreading out. I mean, quantum sensing is creating atomic clocks so unbelievably precise, they can detect the pull of gravity changing over the height of a single person. It's letting us map the inside of the Earth to find water and minerals. It's even creating the possibility of these huge networks of sensors that could basically act as a single continent-sized scientific instrument.
And there isn't just one kind of quantum sensor. It's not a one-size-fits-all thing. Researchers are building out a whole toolkit of different platforms. Some use individual atoms because they're so stable, and those are great for making hyper-accurate clocks. Others use tiny defects in solids for super high-resolution imaging. And then you've got superconducting circuits, which are being used in the hunt for dark matter. The right tool for the right job. So the potential is clearly enormous. But there's a pretty big reason these amazing devices aren't just sitting in your smartphone yet. Moving from a perfect, clean laboratory environment into the noisy, messy, real world, well, that's a massive challenge. So what is it? What's the one big hurdle that all these researchers are laser focused on overcoming? What's the kryptonite to these incredible quantum superpowers? Well, the answer is just one word: decoherence. Those super delicate, entangled quantum states that give us this amazing advantage, they are incredibly fragile. The tiniest vibration, a small change in temperature, a stray magnetic field from, the wiring in the wall, any of it can disrupt the system and just erase its quantum edge, making it collapse right back to that old standard quantum limit. And overcoming decoherence isn't just a quantum physics problem, not at all. It is a monumental engineering challenge. It's going to take physicists, material scientists, and classical engineers all working together. They have to develop new materials, better ways to shield these things, and just clever protocols to protect these fragile states and build devices that can actually survive outside of a perfect lab. But despite all those challenges, the path forward is really clear. Quantum sensors aren't just some small incremental improvement. No, they represent a fundamental shift in how we actually perceive reality. They are a new keyhole, letting us see things that were invisible and measure things that were immeasurable. And they promise to unlock a whole universe of discoveries that are, for now, completely beyond our imagination.